Welcome to 7.07, last class of the year. So we're going to be finding and interpreting what's called the margin of error, and we're going to use margin of error to analyze certain claims about some different types of situations. So let's go ahead and get started. Alright, so imagine that we are at the same high school we were yesterday, and we're taking a bunch of samples of 30 randomly selected girls from this high school. We know 40% of girls at the high school play a sport. What's the dot plot of the sample proportions going to look like? So what I want you to do is think about what is the shape, where's the center going to be, maybe sketch a quick graph of it, and we'll talk about it in just a second. Alright, so hopefully, as we talked about yesterday, you realize that the true proportion is 0.4, and so the center of the data should lie at 0.4. And if I take enough of these random samples, we should realize that most of them are going to be around 0.4, and as I move away from 0.4, there's going to be less and less proportions that are farther away from 0.4. In other words, it might look something like this. And as we can see here, right, they're not all going to be at 0.4 because they're randomly selected, and so some of them are going to be a little less, some of them are going to be a little more. But we do see that the proportion that is most common are going to be proportions that are closer to 0.4, and what we'd like to do is kind of get an idea of how spread out the data is. So it looks like the mean is pretty close to 0.4. Let's go ahead and compute the standard deviation. So remember that the standard deviation, if we know the true proportion, is going to be the square root of p times 1 minus p divided by the sample size, n. So go ahead and pause the video and compute that quickly. Alright, so we see the standard deviation, 0.4 times 0.6, p times 1 minus p divided by 30, and we get about 0.089. Or in other words, one standard deviation away from the mean, if the mean is 0.4, one standard deviation away is going to be about 0.49, and one standard deviation below is going to be about 0.31. Okay, and now we might consider, okay, well, how much of the data that we have here is going to be within one standard deviation, and how much of the data is going to be within two standard deviations? So what I want you to do now is decide how much of it is within one standard deviation, maybe just draw a line that encompasses all of them that are within one, and then all of them that are within two. Okay, so there is the amount of data that's within one standard deviation, right? And that looks like a good portion of the data. Now what I want you to do is go ahead and decide how much of the data is within two standard deviations. Alright, so here is the amount of data that's within two standard deviations. And you'll notice that this is a pretty good chunk of the data. And in fact, what we've talked about previously is that this data here is mound-shaped and approximately symmetric. And so this could be approximated using a normal distribution. And what you'll remember with a normal distribution is most of the data is going to lie within two standard deviations of the mean. So if I were to approximate this with a normal curve, and I did an okay job there, it could have been better obviously, most of the area under the curve is going to be within two standard deviations. In fact, with a normal curve, the amount of data that's within two standard deviations is 95%. So let's say that you're going to pick a sample proportion from this group of sample proportions that you discovered. And you want to be 95% confident in the value that you're going to get. Well, 95% of the data is within two standard deviations of the mean. So knowing that the mean is 0.4, if you are you're 95% confident that the one you pick is either going to be 0.18 greater or 0.18 less, meaning that you're going to be 0.4 plus or minus two standard deviations. And notice that I rounded this here to 0.09. So I can be 95% confident that if I pick a random one of these dots, it's going to be within what's called a confidence interval. So this confidence interval is the mean plus or minus two standard deviations. And since that is going to hold 95% of the data, I am 95% confident that if I picked one, I would get something that's in between 0.4 minus 0.18 and 0.4 plus 0.18. Now this piece in particular, this plus or minus 2 standard deviations, right? Where did I get this from? I did 2 times 0.09, which is a standard deviation. And so if I were to pick a random one of these sample proportions, I would be 95% confident that it is within 0.18 of 0.4. Right, so now let's take a look at a more realistic situation, because you may have picked up on the fact that there is a particular aspect of this situation which is not very realistic. All right, suppose that we don't know the true proportion for girls that play sports. So you take a random sample of 45 girls and find that 17 of them play sports. What I want you to do is give a confidence interval for where you expect the true proportion to lie. So try this on your own. You have all the tools you need to figure this out. Take a look at some of the work that we've done previously to give you a clearer idea. Okay, so notice here that all we have to go on is this random sample that we took. And so from our random sample, we can compute the proportion from our random sample. Okay, so this is not the true population proportion, right? The true population proportion we would denote as P. Here we have a sample proportion, which we will denote as P hat. Okay? And so our estimate is that 17 out of 45 actually play sports. And so if I were to round that, that is going to be approximately 0.38. Okay. Now, would you want to bet your life that this sample is actually giving you the true proportion? I would hope not, right? But is there a way that we can estimate how much higher above or how much lower below we'd have to go so that we were really confident that we knew about where the true population proportion would lie? And in order to do that, we need to think back to how we constructed our margin of error. How did we compute our confidence interval? And the way we did that is by finding how many standard deviations, what the standard deviation was, and then thinking about 2 standard deviations above and below the mean as encompassing most of the data. Here, of course, we can't find the true standard deviation. So we're going to find the sample standard deviation, which is called the standard error. And we talked about this yesterday. So we call this the standard error. This is just an estimate of the standard deviation. And the way that we compute that, we'll call that S hat, is the square root of my sample proportion, 0.38, times 1 minus my sample proportion, 0.62, divided by my sample size, which is 45. And so here, this is approximately 0.07. Okay. So think about what we have here. We have an estimate of our proportion, about 0.38, and we have an estimate of our standard deviation, 0.07. So if we wanted to make an interval that we were really confident the true proportion lay within, we would want to move at least 2 standard deviations above and 2 standard deviations below my sample proportion. So my confidence interval is 0.38 plus or minus 2 times my sample standard deviation, or what's called my standard error. Standard error. Okay? So this is my standard error, and 2 times the standard error is called the margin of error. Right? The reason we use the term margin of error is because this is the amount that we need to go above and below so that we feel confident that we have included in that interval our true proportion. And so this is equivalent to 0.38 plus or minus 2 times 0.07 or 0.14. In other words, it is our estimate, we are 95% confident that the true value of P the true population proportion is less than or equal to 0.38 plus 0.14, which is 0.52, and greater than or equal to 0.38 minus 0.14, which will be 0.24. So we are 95% confident that this statement is true. In other words, that P is less than or equal to 0.52 or greater than 0.24. And that should make sense, right? Based on your sample, you got a sample proportion of 0.38. Well, you know what? I don't think that's exactly right, but I bet it's pretty close, right? I wouldn't be very sure that my true proportion was 99% if I took a sample and got 38%. Okay? So hopefully this made sense. We will take a look at some more examples tomorrow.